MOS IV characteristics. In this session, we analyze the generation of transport of charge in MOSFETs as a function of thermal voltages. Our objective is to derive equations for the IV characteristics such that we can elevate our abstraction from device physics level to circuit level. Threshold voltage. Consider an FT connected to external voltages as shown in figure A. What happens as the gate voltage Vg increases from 0 since the gate and the substrate form a capacitor. Here you can see the figure. A MOSFET driven by a gate voltage B, formation of depletion region C, onset of inversion D, formation of inversion layer. As Ig as Vg becomes more positive, the holes in the P substrate are repelled from the gate area, leaving negative ions behind so as to mirror the charge on the gate. In other words, a depletion region is created. Figure B. Understand, under this condition, no current flows because no charge carriers are available. As Vg increases, so do the width of the depletion region and the potential at the oxide silicon interface. In a sense, the structure resembles two capacitors in series, the gate oxide capacitor and the depletion region capacitor. Figure C. When the interface potential reaches a sufficiently positive value, electrons flow from the source to interface and eventually to the drain. Thus, a channel of charge carriers is formed under the gate oxide between S and D, and the transistor is turned on. We also say the interface is inverted. The value of Vg for which this occurs is called the threshold voltage, VTH. If Vg rises further, the charge in the depletion region remains relatively constant while the channel charge density continues to increase, providing a greater current from S to D. In reality, the turn-on phenomenon is gradual function of the gate voltage, making it difficult to define VTH unambiguously. In semiconductor physics, the VTH of an FET is usually defined as gate voltage gate voltage for which interface is as much n-type as the substrate is p-type. It is proved that VTH is equal to ohm ms plus 25F plus Q dep by QoS by CoS, where ohm ms is the difference between the work functions of the silicon gate and the silicon substrate. Phi f is equal to kt by q natural log n sub by n I. Q is the electron charge, n sub is the doping concentration of the substrate, Q dep is the charge in the depletion region, and Cox is the gate oxide capacitance per unit area. From p-n junction theory, Q dep is equal to root over 4q epsilon Si mod phi f n sub, where phi epsilon Si denotes the dielectric constant of silicon, since CoS appears very frequently in device and circuit calculation. It is it is helpful to remember that for TOX similar to 50 ohm, COX is similar to 6.9 FF by new meter square. The value of COX can be then scaled proportionally for other oxide thickness. In practice, the native threshold value the native threshold value obtained from the above equation may not be suited to circuit design. Example, VTH equals 0. The device does not turn off for VG greater than equal to 0. For this reason, the threshold voltage is typically adjusted by implantation of dopants into the channel area during device fabrication, in essence altering the doping level of the substrate near the oxide interface. For example, as shown in figure, if a thin sheet of P+ is created, the gate voltage required to deplete this region increases. Here you can see the figure, implantation of P+ dopants to alter the threshold. The above definition is not directly applicable to the measurement of VTH. In figure A, only the drain current can indicate whether the device is on or off, thus failing to reveal at what VGS the interface is as much n-type as the bulk is n-type. As a result, the calculation of VTH from IV measurements is somewhat ambiguous. We return to this point later, but assume in our preliminary analysis that the device turns on abruptly for VGS greater than equal to VTH, and the turn on phenomenon in a PMOS device is similar to that of an FTs, but with all of the polarities reversed as shown in figure. The gate source voltage becomes sufficiently negative as inversion layer consisting of holes is formed at the oxide silicon interface, providing a conduction path between the source and the drain. Here you can see the figure, formation of inversion layer in a PFET. Thank you.